Vulkan is extremely explicit. Everything must be spelled out. Most of the time that's pretty good, but sometimes this can be pretty painful. In this video I want to talk about one particular painful aspect, descriptor sets and pipeline layouts. If you work with Vulkan, you know the pain. If you haven't, let me show you what you're in for, and more importantly, how to avoid it. Let's say we want to render something in Vulkan. For that to happen, we need to create a pipeline, which encapsulates all the state needed for drawing. And that's a lot of state. One critical part is the pipeline layout. Think of it like an interface in object-oriented programming. It tells the Vulkan driver which resources can be bound to the shader when drawing. You can see in this shader that it binds a few resources. It has a uniform buffer with the camera data, the model transforms stored in a storage buffer, a color texture for the models, and push constants with per instance specific data. It's a pretty straightforward shader. Now let me show you the Vulkan code that is needed to create a pipeline layout for this. First, we create a binding for the uniform buffer, then a binding for the instance storage buffer. We group these in a descriptor layout binding. Next, we create a descriptor set layout. Then we create a second descriptor set layout for the color texture. Why a second set? Because we update the color texture at a different frequency. Finally, we define the push constant range for the push constants. With all this information, we can finally create a pipeline layout. Now that's already a lot of code, and that is only one shader with a few basic resources. This is a maintenance nightmare. If I add one texture to my shader, I need to come here and add another binding struct, update the bindings array, increment the bindings count every single time. And if I make a mistake, at best I get validation errors at runtime, otherwise it's just undefined behavior. Let me show you how I solved it. Now the answer to this problem is automated shader reflection. I generate the reflection data at compile time and then use it to build pipeline layouts automatically. Here's how my shader compiler works. First I compile glsl to SPIR-V. SPIR-V is an intermediate binary format for shader languages, and it's the format that Vulkan expects. I use the library glslang for that. I then use a library called SPIR-V cross to read all the resource information from the generated SPIR-V. I start by creating the SPVC context and set up some initial state. Next I create a SPVC compiler. All the reflection data gets stored in a struct called a reflection shader. Reflection shader contains all the bindings that could be reflected from the shader, the descriptors, the push constants, and the vertex attributes. I store the data in hard-coded arrays because that makes serialization later a lot simpler. The magic number and the version are needed for serialization as well. The magic number is just a sanity check when loading, and the version will allow in the future to support updates to the format. The first thing that gets reflected from the shader are the vertex attributes. I store the location, type, and name. Next I reflect the push constants. I store the set number, binding, offset, and size. In addition, each property of the push constant struct gets stored as well. This is needed because all the OpenGL versions only support name and uniforms. There is no notion of uniform buffers there, so to emulate push constants with all the OpenGL versions, the name, offset, size, and type for each property gets stored in the reflection data. In case you wonder how I create the shaders for OpenGL, I use SPIR-V cross as well for that. It can generate OpenGL GLSL code from the SPIR-V format, and it's surprisingly readable. In the next steps, the reflection of uniform and storage buffers happen. This works very similar to what you've already seen so far. Finally, I reflect the textures. Now here's a cool thing, I store everything in a simple struct, as already said. No pointers, no dynamic memory. And because of that, I can simply dump it straight to disk. It's only one file write, and one read later. It's pretty fast and simple. Let's take a look at the Vulkan code that uses the reflection data to automatically generate the pipeline layout. The pipeline layout gets created when the user creates a new shader by calling gshaderalloc. The backend specific function for Vulkan in this case is vk_shaderalloc. We start by generating the path to the shaders on disk and then loading them. Notice that while reading the shader from disk, I also load the reflection data. The reflection data is stored in a separate file that has the same name as the shader, but just with a different extension. After the shader modules for vertex and fragment shader got created, I start building the pipeline layout. I iterate over the reflection data from the vertex and fragment shader. There's one critical thing that needs to happen here. The vertex shader reflection module might contain the same resources as the fragment shader reflection module. That happens if the same resources get used in vertex and fragment shader. On top of that, the bindings of one descriptor set might be split between vertex and fragment shader. That's why I perform merging of the resources. At the end, VK descriptor set layout data contains the merged descriptor sets. Push constants are a little bit simpler because there can only be one push constant in the shaders. It's just important to set the right shader stage flags on them. As a last step, I sort all the descriptor sets to ensure they have the same order across different shader pipelines I create. This is useful if you later want to generate good hashes from the pipeline layout. It's not something I use right now, but can be very useful when creating a more advanced material system to ensure instancing of the pipeline layouts. The final step is creating the Vulkan objects from the data. First I generate the descriptor set layouts, and then finally the pipeline layout. I store the pipeline layout on the shader for later use when creating the actual pipelines. I've already shown this briefly in the other videos, but here is how it looks like creating a pipeline. The first step is allocating the shader. I just specify the file names of the vertex and fragment shader. This will internally create the Vulkan descriptor set layout and pipeline layout as shown. The next step is creating a G pipeline create info struct. Set the shader and some rendering state, and then allocate a new pipeline. As you can see, it's pretty straightforward in just a couple lines of code. No manual descriptor set layout code, no push constant setup. The system reads the reflection data and handles everything automatically. Quick note about OpenGL. In OpenGL it's even simpler because we don't need pipeline layouts at all. But we still need some information like uniform and vertex attribute locations. On top of that, as said earlier, all the OpenGL versions do not support push constants or uniform buffers. That means I need to emulate them. To do this, I leverage the reflection data to figure out which uniforms I need to set and where I can find data in the push constant struct. In glcmd set push constants, I extract the right data from the push constant struct and set the uniform in the right location. And that's how I tame part of Vulkan's complexity. This speeds up development quite a bit and removes an entire class of bugs. There's a second part to this, and that's how to generate the descriptor sets at runtime with the actual resources. You can imagine how I use reflection data for this as well. I may cover this in another video in more detail. If you found it helpful, drop a like and subscribe. Let me know in the comments what other topics you'd like to see. Thanks for watching.